In this video, I'll be talking about two basic counting principles, and here I'll be talking about the sum rule and the product rule. So before I state sum rule and product rule, let's have this question. And this question says, how many ways can a pair of dice fall? And in this, most common answer that the student give is 36 ways. So let me to first write most common answer is 36 ways. And here when somebody gives the answer as 36 ways, so it is assumed that the dices are distinguishable. They are different. And so in that case, they consider all possible outcomes. So let me to write these outcomes to clarify how I got this 36 ways. But also since I am mentioning that this is a discussion question, so I am claiming that this answer may not be 36 ways, but the correct answer could be considered as 21 ways. So let's see how did I got this 21 ways. I'm considering, because it's a pair of dice, so there are possible that we consider all possible outcomes in the sum outcome form. And for this, there are only 11 ways, because the sum can be minimum 2, it can be 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. This is the maximum possibilities for the sum. Whenever two dice are fall, or we may say a pair of dice falls, because the least number on each die is 1 and the maximum number is 6. So if both the dice have 6, the sum is 12. And if the minimum possibility comes on the two dice, the minimum possible sum is 2. So we write examples for the two category. One where I am considering this as 21 ways, and here I have considered dice are indistinguishable. So when I consider that the dice are indistinguishable, that means we are only looking at the two dice and their visual outcome, what we see as an outcome. Whenever two dice are fall and say on one dice you got 1 and on another dice you got 2, so you will consider that the visual outcome is 2, 1 or 1, 2. This will not be considered as a separate pair. We'll just simply say that one dice is showing us one outcome and another dice is showing us as 2 outcome. Whereas in the elementary event, we consider 36 ways, and that is why I said that most common answer is 36 ways. And here we have considered this as distinguishable dice, which means that we do bother that on first dice 1 appear and second dice 2 appear, or similarly if 2 appears on the first dice and 1 appear on another dice, so these two outcomes are considered as different. So now keeping these things in mind, that we are writing for distinguishable or indistinguishable, whenever the sum is 2, then the possible is only 1, 1, and here rather than avoiding that into ordered pair, we'll simply write 1 and 1. So two dice are giving us the option 1 and another dice is also giving us the option 1. Here one dice is giving one option, another dice is giving two option. Here we have 1 and 3 and another possibility is 2 and 2. Similarly, we continue to finding for the all others. And for this, I will write it as a pair so that the order does matter, 1 and 2 and 2 and 1. And we continue doing this for the rest of the sums, and we get. So whenever we want to know about answers about how many ways are there to count something, we must be sure whether we are counting indistinguishable or distinguishable. If there is no guarantee, then both the answers should be given. So now let us look at the sum rule and the product rule. So in the sum rule, the sum rule can also be known as the principle of disjunctive counting. So here we assume that if a task can be done in n1 ways and second task can be done in n2 ways and the mth task can be done in nm ways, then the total number of ways are n1 plus n2 plus up till nm. And of course we have considered here that if these tasks cannot be done at the same task, if these tasks cannot be done at the same time, cannot be done at the same time. So we may use this simple notations considering that these are tasks, or we may define as n1 ways for the event e1, n2 ways for the event e2 and nk ways for the event ek, and these events are occurring pairwise disjoint. So that means if different events to occur pairwise disjoint, so there is nothing common between these two, then the number of ways for at least one of the event to occur. So we are saying at least, that means all can also occur. To occur is n1 plus n2 plus nk, that is summation of ni, I being from 1 to k. We can also define the sum rule in the set theoretic notation as, so here we consider A1, A2, AK be any k finite sets, and we have assumed that these are pairwise disjoint, so which means AI intersection AJ is equal to empty whenever I is not equal to j. So the cardinality of the union of these AIs is same as this. Here it is simply written in the expanded form, union I varying from 1 to k. This is same as summing the cardinality of the individual set. So this is how we apply the addition rule in the set theory. Now let me to consider a simple example. Now in this example the question asks, suppose that one reaches city Q from city P by sea, air and road, and suppose there are 2 ways by sea, 3 ways by air and 2 ways by road, and we want to find the total number of the transportation ways. Now we can see that this is disjoint if I consider sea as one of the set, air as the another set and road as another set in the set theoretic form, or if I consider sea as the one event, air as the another event, road as the separate event. So there are 3 events, and of course you cannot club sea with air, so these are pairwise disjoint. So here we will apply the addition rule, so or you can say by addition principle or by sum rule. So we will simply add, there are, suppose I want to reach from P to Q, there are 2 ways by sea, and say suppose by sea I am just showing it by the solid line, then 3 by air, so let us show that it by the dotted line. So there are 3 routes by the air, and then there are 2 by the roads, and for the road I will, let's say I am just using this notation, a little more bold, but again a dash line. So in total how many ways are? We simply need to count them. So the total becomes 2 plus 3 plus 2, and that is we get 7, and this is how we get the total transportation ways, that is 7 ways. Now in this example I want to find the number of ordered pair x comma y of integers such that x square plus y square less than or equal to 5. And so in this case, suppose I want to just consider this in the set theoretic form, and I want to make a systematically count. So I'll define a set x comma y which consists of pair, and x and y belongs to integer because the condition says that they belong to integers such that x square plus y square equal to I. So the sum is equal to some integer I, and let me to call this as s of I. So now if you take S0, so this will consist of only one possible pair 0, 0, because 0 square plus 0 square is equal to 0. If you consider S1, so here you consider all possible x and y whose square sum is equal to 1. In this case we will get 1, 0, minus 1, 0, we'll have 0, 1, and we will have 0, comma, minus 1. So this way we are counting in a systematically way. For S2, we can consider 1, 1, where the sum will be equal to 2, minus 1, 1, and then you will have minus 1, minus 1. Now, if you want to consider for S3, now you can say you cannot find any square sum which is equal to 3. So this is not possible, and hence in this case, we will simply write that S3 is empty. For S4, we have the pair as, and for S5, we have. And so by sum rule, we can simply say that the total number of cardinality of the set, that is summation of SI, individual set, I varying from 0 to 5. So you sum how many elements are there in the each of these set. So once we sum in the each of these set, this become 1 plus 4 plus 4 plus 0 plus 4 plus 8. That is equal to 21. We could have counted this in the directly way also. Say you want to directly write x and y in a random way, then also you can count for this. But here what I am trying to answer is that whenever you count in a very systematic way, this will allow you to write the combinatorial proof as well. Now we define multiplication or the product rule, and this is the principle of sequential counting. So here suppose a procedure can be broken down into a sequence of m tasks. Say n1 ways to do the first task, n2 to do the second task, and nm to do the mth task, then the total number of ways is the product that we get it from the product, that is n1 into n2 followed by nm ways. Or we may define that, assume that an event E can be decomposed into m ordered events. So ordered means they are in the sequence of the in which they occur, E1, E2 up till EM, and there are N1 ways for the E1 to occur, N2 ways for E2 to occur, and Nm ways for EM to occur. Then the total ways for E to occur is n1 into up till nm, and that is the symbol for the product, just like we use for the summation, I varying from 1 to m, ni. Or simply in the set theoretic notation, we can rewrite this definition as product ai, which is equal to a1 into up till am, and this is the ordered pair notation that we use in the set theoretic form, where each ai belong to capital of ai for I varying from 1 to m. This denotes the Cartesian product of the finite set. So whenever we say this is Cartesian product, that means order is already considered here, and hence the total number of elements in the set, main set, which is equal to the product of the AIs, that is equal to the cardinality of the individual set, and then we take the product. So this is how we write the multiplication rule. Now let's take an example and apply the multiplication rule. Now in this example, we want to reach a city D from city A, and one has to pass through city B and city C. So this is like an order or in a sequential count. If there are 2 ways to travel from A to B, and there are 5 ways to travel from B to C and 3 ways to travel from C to D, then we want to count the total number of possible ways from A to D, or reaching city D from A. So in this case, let's look at the diagram. We are having at A and we want to reach to the city D, and in between there are 2 cities B and C. The question says there are 2 ways to travel from A to B. So let me to show you the 2 ways. Then there are 5 ways from B to C. So here we have to draw the 5 ways. So let us take the 5 ways. So these are the 5 ways, and then there are 3 ways from C to D. So we will have again 3 ways from C to D. And now I want to count the total number of possible ways. So now from the diagram also you can see that this is a sequential counting. So if you start looking at any one of the, and then again you start looking at this, and then you choose another path, and then you choose this path. So this depends upon the ordering also. So here by multiplication rule, or we can simply say by the product rule, let us apply how many possibility are there for the A case. So there are 2 ways, and for the B to C we have 5 ways, and from C to D we have 3 ways. So in total there are 30 ways by which a person can travel from A to D. So now before moving to next set of examples, we must need to set up the convention, while as the same we have discussed in the discussion question. And now since we know the sum rule and the product rule, people, whenever we consider the people in the counting, people are distinguishable. So we don't consider them to be indistinguishable. People are distinguishable. And in case you consider simple dice, or maybe you consider apple, or maybe you consider oranges, or maybe you consider A's, or you consider some letters or some colors, reds, these all are indistinguishable unless otherwise mentioned. So it has to be very specific that if it is mentioned that these are distinguishable, only then we consider. Otherwise, for the general counting principle, these are considered to be distinguishable. So for example, you may have 2 dice, and here you may say that one dice is of the green color and the another dice is of the, so we'll take another dice is of the color red. So in that case, this is already distinguishable because the color of the dice is mentioned. So these are distinguishable. But say that we simply consider that there are 2 pair of dice, and then you want to know certain outcomes. In that case, we will consider them to be indistinguishable. So considering these in mind, an object can be distinguishable and indistinguishable, and considering the sum and product in mind, let's take few more examples. So in this first problem, how many ways are there to pick one student from 6 boys and 8 girls? And as we just have discussed that the people are distinguishable. So here we'll apply the sum rule, and there are possibilities 6 boys and then you have 8 girls. So in total there are 14 ways. We will consider them to be distinguishable. In this second question, how many ways are there to pick one piece of fruit from 6 oranges and 8 apples? So now there are 2 different events, or maybe you can say there are 2 different fruits. But we just discussed that oranges itself cannot be distinguishable. So we'll consider 2 categories. Either the fruit could be orange or it could be apple. So there are only 2 ways. So we may consider either the fruit is orange. So because we have to pick only one piece of fruit. So either the fruit is orange or it is apples, and we have to take one choice, so there are only two ways. In this question, how many ways are there to pick one letter from 3 A's, 5 B's and 7 C's? Again, there are three ways. This is similarly as I've discussed above. Either we can pick A, or we can pick B, or we can pick C, and the letters are itself not distinguishable. So in question number 4, it asks how many ways are there to pick two letters from 3 B's and 3 G's. So again, we are simply applying the addition principle, but we need to pick two letters. So let's see. Here you need to place two letters. So either the both can be BB, or you can have at one place you can have B and another place you can have G, or at both the places you can keep G. So this means considering these options, so you will have GG plus GB, or we may say BG, and then you can have BB. So there are three ways. So for this we will have three possibilities for writing two letters from 3 B's and 3 G's. Now we look at question number 5 to question number 8, and for the fifth question we have a question as how many ways are there to pick two students from 3 boys and 3 girls. Now this question looks like similar as we just discussed the fourth problem, but here the problem is that persons we consider as distinguishable and the object we do not consider as distinguishable. So in this question we will consider that suppose the first student that we choose is from only boys. So again, but there are 3 boys, so that means there are 3 possibilities for the boys itself. Then for the 3 possibilities for the girls, considering that all the boys are distinguished, they are different and girls are different, or there could be an option that we first select boy and then followed by another student is selected as the girl. So this is for the 2 student when one is selected as boy and another is selected as girl. This is also where one student is selected as boy and another student is selected by girl. So this is addition principle. Then here we have applied the multiplication principle, and again in total we apply the addition plus multiplication principle. So we get in total 3 plus 3 plus 9, that is 15 ways. In question number 6, we ask how many ways are there to pick 5 oranges from 6 oranges. Again, considering oranges are not different, so there is only one way. So we can pick up any 5 oranges from 6 oranges. In question number 7, how many ways are there to pick 5 girls from 6 girls? Again, girls are in the question, so we consider persons are distinguishable. So here we'll consider 6 ways. Similarly, in question number 8, how many ways are there to pick one girl from 6 girls? Again, for this we have 6 ways, and if we look at these two questions in together, question number 7 and 6, and although at this moment we have not defined the definition of the combination, which is ordered permutation, we are still on to addition and multiplication rule. But say here in this question I would have considered NCR. So in this notation, out of 6 girls we are selecting 5 girls, 6C5. So this will allow me to write 6 factorial upon 5 factorial, 6 minus 5, that is 1 factorial. So we see that we get 6 ways. And here we will apply 6C1, which means again we are going to get 6 ways. So this will allow me to write NC N minus R. So if I look at these two rules together, so these two questions are same, asked in a different manner, and here we have used the property NCR is same as NC N minus R. So this we will explain in the coming up videos. So in question number 9, it has asked how many ways are there to pick some piece of fruit from 9 oranges and 6 apples if at least one piece is picked. So the question is on at least, that means we can pick more number of pieces. So for this we'll write this into 2 sets, and here I'm considering 0, 1, 2 up till 9. So there are 9 oranges. So 0 is assigned if no orange is picked. So if no orange is picked, and maximum 9 oranges are available. So I'm considering it from the point of view a universal set. And S2 is whenever I'm considering the set for the apple. So if no apple is picked, it is 0, and maximum we can pick 6 apple. So from here you can see that there are 10 choices. So we can have 10 choices, and here we have 7 choices. So now total number of choices in the set S1, S2 by the multiplication rule is 10 into 7, which is 70. And here I want to exclude this choice 0, 0, so that no apple and no orange. So this choice I am excluding because at least one fruit has to be picked. So in total number of choices which is relevant to our problem is 70 minus 1, that is 69 ways. So out in 69 ways we can select at least one fruit from the available 9 oranges and 6 apples. In question number 10 it asks to determine the number of positive integers that are factors of the number this, and here we notice that 3, 5, 11 and 13, these all are primes. So when these all are primes, any divisor of these prime will also be of the type this. So any divisor d, and let's call this number n, which is equal to 3 to the power 4 into 5 square into 11 raised to power 7 into 13 raised to power 11. So any divisor d of n will also be of the same form. So here we'll consider 3 to the power I into 5 to the power j into 11 to the power, let me to call this as k, into 13 to the power l. But of course there is a bound on I cannot exceed then 4. Similarly, j cannot exceed then 2 and k cannot exceed then 7 and l cannot exceed by 8. So now we count how many choices are there for I and how many choices are there for j and how many choices are for l and available for l. So multiplying these options, so we'll have 5 into 3 into 8 into 9, and that becomes 1080 ways. So these are the total number of ways which will allow us to write the number of positive integers that are factors or that divide this number. In fact, this is a problem which is associated with the tau n function. Tau n is the arithmetic function defined in number theory, and this counts the number of divisors. So here we say this counts the number of divisors of n, number of positive divisors of n. So the counting principle comes in the same proof, writing n in the prime factorization p1 to the power k1 up till pr to the power kr, and then we see if d divides n, how many d exist for this case. So we look at the exponent here, k1 up till kr. Any divisor d of n will also have the same p1 to the power a1 up till pr to the power ar, and then of course ai's cannot exceed these ki's for 1 less than I less than or equal to r. So we can see from this one, ai's has ki plus 1 choices, ki plus 1 choices. Each ai has ki plus 1 choices, and this is how we establish the proof for the tau n function which is used in number theory. But here again, since we are interested in noting the counting, so we get 5 into 3 into 8 into 9, 1080 ways. In 11th problem, let computer password consist of a string of 6 symbols. So that means each password should have 6 symbols taken from the digit 0, 1 to 9. There are 10 choices for the digits, and the lowercase letters a, b up till z or z. So which means there are 26 choices for the letters. So in total, if we consider u, this is the set of all computer passwords. So suppose I am considering a universal set which consists of all computer password. Now the question says that how many computer passwords are there that have a repeated symbol. So to know the repeated symbol, we will attack it from the counter side. I'll first calculate a set which do not have a repetition. So let me say A, this is the set of computer password with repeated symbol. This is what you want to calculate with repeated symbol. And if I just simply write A bar, which means this is the set of computer password with no repeated symbols. So obviously to calculate A bar, we can do it u minus A. If I know what is the cardinality of the set u and subtracting the cardinality of the set A, I can find the cardinality of the set A bar. So for u, we see the cardinality of the set. Here everything is possible. We want a 6. We want string of 6 symbols. So that means we want to put 6 places. 1, 2, 3, 4, 5, 6. Say we want to place 6 symbols here. And since we do not put any restriction in the universal set, there are 10 digits available and there are 26 alphabets available which are lower digit. So in total we have 36 symbols which we can place in each box and then further create a password. So here, which means 36 into 36 up till 36. And how many possibility we have? We need 6 boxes. Or we need 6 placements, 6 symbols. So that means we have 36 raised to power 6. And for A bar, here we have said that no repetition is allowed. So now I am taking those where no repetition is allowed. So that means if for the first position we have 36, for the second we only have 35 choices, and then we have 34 choices. I am eliminating the choice which we have already used. So this means no repetition is allowed. There are 6 symbols. So this will give me the quantity 14024102440. And to know how many sets are there in the computer password with repeated symbol is if I use this as A, which is U minus A bar. So I'll rewrite this formula in this format. So here we can calculate A, that is cardinality of the set A is the cardinality of the set U minus the cardinality of the set A bar. And so from here we can calculate this one, that these are the number of choices, or these are the ways in which we can write the computer password with repeated symbols. So in my next video, we'll be talking about permutation and R permutation, which means that we'll be discussing about the distinct order of arrangement of a given set of distinct objects. So which can be with or without repetition. So this I'll explain in my next video.